In this session we see the magnetic field inside a solenoid carrying steady current. Actually, a solenoid is a closely wound laminated conducting wire, closely wound such a way that the radius of the loop will be very small compared to the length of the solenoid. What is that length of the solenoid? We will be knowing from this diagram. And this is the radius of the loop. Then if this is the criteria, then you can treat it as a solenoid. Now assume that the solenoid is of very large length and I consider a point well inside. So to find the magnetic field at this point, we will be using the Ampere's circuital law. And for that I considered a field loop, imaginary loop of PQRS of side length L. This is square loop. Now, according to Ampere's circuital law, we get closed integral B dot dl is equal to mu 0 times the current I enclosed by the loop. This is the basic definition. Now here I rewrite this equation for this particular situation, that closed integral B dot dl for PQRS, this is the closed loop, will be equal to mu 0 times the total current enclosed by the loop. Total current enclosed by the loop. The loop is PQRS. This one. Now total current, when I say total current, it is because there will be more number of turns inside. It's not a single turn. There are more number of turns which is carrying current. Therefore, you have to take the whole current for the calculation. Okay. Now, let us see what is the value of closed integral PQRS B dot dl. And then we find this one. So closed integral B dot dl will be over PQRS will be taken as integration means adding little by little. Therefore, let us take that in this way that integral PQ B dot dl, just for identify or knowing the Ampere's circuital law. So integral PQ B dot dl plus integral QR B dot dl, then plus integral PQ QR RS B dot dl, then plus integral SP B dot dl. This is the value of integral B dot dl over closed loop. Now let us say one by one B dot dl over PQ. Now PQ is coming here outside. Remember, as the current is going through this loop, field just outside the solenoid will be negligible, or you can take it as 0 as the point is very close. Because the field lines will be going like this and completing like this one. Means it forms a loop, but very near to this one there will be no field outside the solenoid. So as there is no field outside the solenoid, B equal to 0, and therefore this part will be cancelled. Become 0. Now what about this one? Let us say B dot dl QR. So QR is coming like this. The field direction is coming, the length is coming like this, you are, but the field is either like this or like this inside the loop, depending upon the flow of current. So field and this dl, they are coming perpendicular to each other, and therefore the dot product will be 0. This part also will be 0. Because dot product of a perpendicular vectors will be 0. Now the same case with S3 also. This also will be 0. Now what about this RS? Let's say RS is coming like this, and the field is also parallel or anti-parallel with what? The RS. So dot product will be maximum and that exists. So this part will be existing and all other three components will be 0. And therefore what we get is instead this will be 0, this also 0, and this also 0, and finally you get this will be equal to integral Rs B dot dl, and B and dl are parallel to each other. This will be equal to B into integral dl, because B is uniform inside, and therefore B into integral dl over Rs, and that will be equal to B into L. This is equation 1. B into L. L we have taken as the side length. Rs is the length, therefore dl will be the length of that side Rs. So left hand side is reduced to a simple value like this. Now the right hand side, mu0 is a constant, but total current enclosed by the loop. For finding that, we have to introduce a new quantity called, let n be the number of turns per length. I am introducing a new term called number of turns per length. Let it be n. Then, as I introduce number of turns per length as small n, the number of turns in this length, SR length, that is the length enclosing or the loop way. So, inside that length, what is the number of turns coming? That will be equal to number of turns enclosing will be equal to small n into L, because L is the length of that. Now, therefore, let me take the total current. Therefore, total current enclosed by the loop will be equal to number of turns into the current I flowing through it. So N into L into I. Here is capital. So this will be the second equation and this will be the first. So you are getting the left hand side and also right hand side. Now put it into the first equation, Ampere circular law applied for this one. What you get, let us see. If I apply that here, you will be getting the equation, that is B into L, this is the left hand side we got, will be equal to mu0 times N into L into I. Okay. So this L and this L is same, that cancels. And therefore, the magnetic field inside the loop, well, inside the loop will be equal to B, which is equal to mu 0 small n into I. This is the equation for magnetic field inside the solenoid. Okay? Magnetic field inside the solenoid. Clear? Now, as we have taken the point, well, inside the solenoid, it's going to be uniform and all that we understood. But there can be one more result you have to by heart, that is, what if this point is somewhere here or here? That means magnetic field at one end of the solenoid. So, field at one end point will be equal to mu 0 Ni by 2. That is half of the field well inside. These two results are very, very important as far as this solenoid is concerned. Okay, that's all.